in this particular semester is all these other different reactions, right? And so the difference is, and so this is stuff that's already in the notes from last week, is that you can use a sodium alkoxide, which is the first example here, to open up the ring to get alcohol and ether. We can use cyanide as the nucleophile, so we get alcohol and cyano group. We can use a thiol that's been protonated in sodium salt to generate a sulfur carbon bond, so like a thioether. And then Grignard reagent can also open them up. And there's a R group on that Grignard reagent, which we covered in the earlier post of this chapter. We learned that take alkyl halide, introduce magnesium that's not oxidized, insert itself, whatever that R group is, will then, of course, be opening up. And then we can also basically generate primary alcohols by reacting the oxide ring with lithium hydride. And again, in all these examples, these two carbons here, these two carbons are the same two carbons in the epoxide ring, right? So that basically kind of sets the stage for this business of the ring opening. Let me make sure that we didn't cover this already. So yeah, so that's the base catalyzed ring opening. And as I mentioned before, this was a reaction that was in the reactions from antiquity handout, is that there's also the acid catalyzed version of the ring opening. And again, this right here is something that we cover in OChem 1. And the reason we cover it from OChem 1 is because in the chapter of alkynes, we learned how to make epoxide rings. Oops. Wait. Are you doing something? Oh, yeah. I see what you're saying. Okay. I'm like, what? Am I speaking too loud? Yeah, so in the chapter of alkynes, we learned that, we can use a peroxy acid to generate these things, and then so it's a great opportunity to introduce this reaction here. So we find out that if you take something like phosphoric acid water, which on the examination is almost always going to be me showing you H3O+, which is acidic water, that causes the ring opening of the epoxide, just like the base catalyzed version using sodium hydroxide. And we generate also the 1,2-diol. And then we can do something a little bit similar, and so it needs to be phosphoric acid and water to generate the 1,2-diol. And the reason for that is because the phosphoric acid water doesn't present an additional nucleophile that can compete with the ring opening, like a mineral acid does. So in this next reaction here, a mineral acid would be HCl, HBr, hydriodic acid. The ion, the bromide, the iodide, the chloride in a mineral acid presents itself as an additional nucleophile that can open up that ring. And so just like what we saw in OChem 1, except we don't go over this reaction, is that you can generate halohydrins like this, all right? And so we probably remember that there is the way to synthesize halohydrins from the alkene synthesis. If you hit a carbon-carbon double bond with Br2 or Cl2 in the presence of water, you generate the halohydrin. But in this case, we can ring open an epoxide ring in the presence of a mineral acid, which by necessity will have water present anyway, to generate this halohydrin, right? So again, this is chemistry that is pretty much right from OChem 1. This is where we introduce the base catalyzed ring opening in the prior bit of notes, and then now I'm just kind of showing you, hey, look, this is the chemistry that we've learned before. All right, so the next reaction that I want to cover is a named reaction, and it is called the Claisen rearrangement. And this chemistry is specific to aryl ethers. So aryl ethers are really easy to synthesize. So all we have to do is hit this with a strong enough base to deprotonate to generate the alkoxide, in this case the phenoxide anion. Sodium hydride is a good reagent to do this. So sodium hydride will deprotonate the aromatic alcohol to generate the phenoxide anion. Sodium hydride, when it does that, traps this as the sodium salt. All right, so now we have the sodium phenoxide, which is a really, really strong and basic nucleophile. So we can then introduce the following alkyl halide. All right, so here's our alkyl halide. And so at this point it's just an SN2, right? The phenoxide anion is going to attack the electrophilic carbon attached to the bromine and trigger the substitution reaction. And we can generate this particular product, which is an aryl ether. Now, once we have the aryl ether in hand, the way it works, and I'm going to draw the reaction separately on the bottom, so that you can see what the pre-organization sort of looks like. Is it the pi bonds will attack this carbon, this pi bond will migrate, the bond holding this oxygen there will then kick downstairs. All right, this is known as the Claisen rearrangement, so I'm just going to put CR, the Claisen rearrangement. In order to trigger this, all you have to do is heat up your aryl ether to 250 degrees Celsius, and this rearrangement will occur automatically, and you can get something like that. All right. So aryl ether is attached to what was formerly the alcohol unit of phenol, going through the phenoxide to put it there, is a way to add that carbon-carbon bond at the ortho position to where that alcohol previously was, and then you end up with something like this. So once you generate your aryl ether, all you have to do is just heat it, it'll rearrange itself, and you can put something at that ortho position. That's the named reaction, which means you might actually see it in the example. Right? And so this is the last reaction for this particular chapter. So this was quite a long chapter. I want to remind you that please use your time wisely in studying these. There's a lot of reactions. If you look at the work that Victor Grenier alone, that was quite a lot of transformations. Okay, so, don't fool yourself about how long it's going to take you to start committing these things to memory. Because on top of that, with the nomenclature, we covered also thiols, we covered ethers and epoxides. Like it's quite a lot of material. So let me give you a minute for those of you to finish writing this down, because now what I want to do is shift gears and go to the chapter on aldehydes and ketones. Now, the good thing about the aldehydes and ketones chapter, a fair amount of the chemistry is stuff you've already seen before, right? And the reason I say that is because one of the ways that we can synthesize alcohols, which means we cover this in the chapter alcohols, is we can reduce the aldehydes and ketones, or we react them with Grignard reagents, right? So those are reactions that overlap substantially. Or we oxidize alcohols. We oxidize a primary alcohol, you get the aldehyde. If you oxidize a secondary alcohol, you get the ketone. So those things are, for the most part, substantially overlapped, which means studying for one chapter will also basically help you study for the material that we're about to cover. So there is an overlap. Where, the overlap, is not very well pronounced is, of course, going to be the nomenclature. All right, so, in case you've been living under a rock since OChem 1, right, these are going to be compounds that have carbonyls. And that carbonyl, if it's in the middle of the chain, is how we remember that those are ketones. If it's on the last carbon of the chain, that's the fundamental difference between an aldehyde. So when we go over these functional groups early in OChem 1, right, what I provide for you is the generic structure of representation of an aldehyde, where the R group at the alpha position to the left of the carbonyl here is any sort of organic spinach, right? If that's a hydrogen, it's still an aldehyde. We just call it formaldehyde. It's two hydrogens at the alpha positions. And then that's fundamentally different than ketones because the ketone is the carbonyl, as I pointed out, in the middle of the chain, where the R groups can be different, they can be the same, right? And then, of course, that sets the stage up for what comes probably right before the final is the chapter on carboxylic acid and carboxylic acid derivatives, because those are also carbonyl-containing functional groups, except now you have an additional hydroxy group at the alpha position, right? So we don't see that here for aldehydes and ketones, obviously. And I think one of the first things that we need to cover are some of the common names for some of these simple aldehydes and ketones. And one that we've seen probably before you even got into organic chemistry is this one here, which I'm sure you've heard of, formaldehyde. And so formaldehyde's a gas. If you've ever worked with a formalin solution, what that is an aqueous solution of formaldehyde just basically bubbled into it. And it's kind of like if you were to make a solution of hydrochloric acid. Hydrochloric acid, HCl, is actually a gas. And the way you make 18 molar HCl is you either generate in situ or you bubble that gas through water and you capture the HCl in the aqueous solution as hydronium. So same thing is true for formalin. So this is actually formaldehyde and it is a gas. So I don't want you thinking that formaldehyde is a liquid, it is not. All right, so formaldehyde is a useful one to learn. And that is its structure. You have hydrogens alpha to the carbonyl on both sides. This one right here is butyraldehyde. Right, the prefix but meaning 4. You look at including the carbon at the carbonyl, at the alpha to the left, there's 3 other carbons, so a total of 4, butyraldehyde. A common one, which we've seen in the chapter of aromatic systems, was this one, which was benzaldehyde. A really common ketone that we get introduced to in organic chemistry is acetone. Right? So that's commercially available to us as an organic solvent that we typically use for cleaning things. Maybe not inside the house, but definitely in the garage. And that's basically a ketone, right? The alpha positions are methyl groups. One of the other groups that we were learning in the chapter of conjugated systems is the following ketone. This is acetophenone. You have 2 of these. The structure is benzophenone. Right. So again, these are not IUPAC systematic nomenclature. These are just common names. Some of them you'll see a lot in the chemical industry. Some of them you're going to see a lot just being in an academic environment. As I said before, acetone, for example, is a really common organic solvent. In my own research lab, we have squirt bottles of this stuff. We buy it by the 5-gallon drum, right? We use it to clean glassware. We use it to clean up molecules. We use it to dissolve impurities or dissolve the type compound, right? So these are just common names. There's nothing systematic about the names by any means. But of course, that doesn't exclude the fact that as we go through ketones and aldehydes, there is systematic nomenclature that we need to commit to memory. So we're going to go over that in the next page after I give you a minute to finish writing down the structures. Is anybody sending this up? All right, let's start with ketones. Now, if we go back to the original sort of hydrocarbon, then ketones are named as alkanones. So the suffix there would go from ane to none. Of course, we say that when we say things like acetones, and it's present in the name ketone, of course. Now, some of the rules is that we're going to be looking for the longest chain. Which incorporates the carbonyl carbon. And it is going to be numbered from the terminus closest to it. Right, so, I mean, that much is not much of a difference or departure from how we've done nomenclature with different functional groups. If we're dealing with cyclic ketones are known as cycloalkanones, where the carbonyl carbon is taken to be carbon 1. And we start from that point, and of course you can number clockwise or counterclockwise depending on the presence of other functional groups to give those functional groups the lowest priority. Give those functional groups, the highest priority. If you go back to the list that we jotted down in the chapter of alcohols, this functional group takes priority over the hydroxy group. Right? Which means it has priority over alcohols. But you can say that it is lower than carboxy. Right? So again, that's me making reference to the fact that in the chapter of alcohols, I pointed out that's the only time I'm going to give you the priority list. All right, so if you didn't get it then, it's in the textbook, you can find it. I would make sure that you remember that. Right? So let me give you some examples. And so I think that given the experience you all have in this class thus far, naming something like this based on what we've just written should be really straightforward, right? It's almost exactly like what we saw for numbering alcohols. If you look at the first example, we had 1, 2, 3, 4, 5 carbons, right? So that's some sort of pentanone. And then if this is the functional group of priority, then I think it's academic at this point to number it like this. Right? There's no point in giving the carboxy or the carbonyl group the number 4. We can give it the number 2, numbering right to left, and so something like this would be 2-pentanone. And then the second one is probably just as easy, right? So if you look at the functional groups that are there, the longest chain that we can make looks like it's 1, 2, 3, 4, 5, 6, 7. So that's going to be hepta something. When we look at the functional groups on that main chain, there's a methyl group, there's a chlorine group. Chlorine is really low on the priority list. And then we have, of course, the carboxy group, the carbonyl group right here. So this is going to be the one that takes a priority. So that's either going to be 1, 2, 3, 4, 5, or 1, 2, 3. So numbering at this stage would be this. Right, and at carbon 6, you can go upstairs if you want, or you can continue going, it's still 7-carbon chain. So that means now we have a methyl group at carbon 6, we have a chloro group at carbon 4, those rules still apply. It's still alphabetical order, so the chloro is going to be numbered first. So this would be 4-chloro, and then we have methyl group at carbon 6-methyl. And then we have to introduce a number to indicate again where the carbonyl is. This becomes 3, and it's 7, so het, unknown. 4-chloro, 6-methyl, 3-heptanone. And then of course the next example would be some sort of cyclopentanone. So there's 5 carbons in that ring. And as we pointed out, that there's really 3 functional groups coming off of that ring. There's the carbonyl upstairs, and then there's 2 methyl groups. And so if we look at the hierarchy again, the carbonyl takes priority, which means no matter how you want to view it, that's always going to be carbon 1. Then it's a matter of, do we number this clockwise or counterclockwise? As I pointed out, the methyl groups can either be at carbon 4 or they can be at carbon 2. Carbon 2 gives them the lowest numbers possible, so this would be the correct way to number this. And so this would be an example of a 2,2-dimethyl, right? So naming this would be 2,2-dimethyl, and then cyclopentanone. And of course, in this case, because it is a cyclic ketone, we don't have to introduce the number to indicate where the carbonyl is because it's assumed that that's already going to be carbon. Right? Now, we might have to include numbers there had there been 2 ketones in the cyclic structure, but because there's only one 2,2-dimethyl cyclopentanone, it's automatic and we're going to give them the 1. All right, so that doesn't matter there. Let's see if we can do this one here. Does everybody think they got it?
Is it 2-ethyl, 3-methyl cyclohexanone?
This is true. Yes. Carbon 1, 2, 3. You said 2-ethyl, right? 3-methyl.
2, 3.
Cyclohexanone.
And 6.
Yes. I was just going to ask you about stereochemistry. There is stereochemical information provided. Groups at 2 and 3 are cis. Absolutely. So cis 2-ethyl, 3-methyl cyclohexanone is correct. Good job. Does anybody have any questions about these problems for you? Yeah. I think these ones are pretty straightforward. And you got to remember the stereochemistry. Does anybody still need this up? All right, let's move to aldehydes. All right, so the only difference between the suffix of alcohols and the suffix aldehydes is that it's an AL instead of an OL. I'm bringing this to your specific attention because I'm going to give you an answer there where it's OL on the examination. We're trying to confuse you. Because whenever there's a one-letter difference, that's always a potential pitfall that I'm going to try to trip you up on, all right? So alkanes, we name aldehydes as alkanals, all right? And then I think at this point, it's the same sort of situation, right? We're looking for the longest chain, and whatever that longest chain is, it needs to incorporate. So the longest chain incorporates the terminal carbonyl, because the terminal carbonyl is the functional group for the aldehyde. It's the carbonyl on the last carbon of a chain, which means alpha to one part of that carbonyl is another carbon, the rest of the organic spinach, whatever that is. Alpha in one of the directions has to be a hydrogen, right? That's the indicator that you're dealing with an aldehyde. So the longest chain incorporates the aldehyde group. And if this is the functional group that takes priority of everything on the molecule, then it's this carbon is numbered as C1, right? And again, it comes down to, is this the functional group that takes priority? If it's the functional group that takes priority, then the aldehyde carbonyl carbon is number 1. This statement on cyclic aldehydes is one that I think trip up a lot of people. Okay, the suffix for cyclic aldehydes is carbaldehyde. And I'll give you an example of that, carbaldehyde. I see that particular problem on the exam always missed. And the reason for that is because, in my opinion, there's other examples that seem more intuitive. And you might forget the carbaldehyde is the correct one. So the naming is really not that complicated. If this is a 2-carbon containing aldehyde, then ethanal is enough to describe it. Let's see. Right, here's another chain. Longest chain here is 1, 2, 3, 4, 5. All right, we see that there's an aldehyde functional group. The other functional group there are just some organic spinach, methyl group, ethyl group. All right, so it does take priority, which means this automatically gets carbon 1, and we'll be numbering like this. And carbon 4, you can go up if you want, doesn't matter, there's a methyl group at carbon 4. Ethyl group at carbon 2. So this would be alphabetical order, 2 ethyl, 4 methyl, and then 5 is pent, pentanal. And then just to give you an example of one that I see missed a lot, not exactly this example, but the use of the term carbaldehyde, right? So, you know, if this was cyclopentane, cyclobutane, cyclopropane, no matter what it is, cycloheptane, right? The naming of these things is really straightforward. All we're going to do is write the name of what the ring is. So in this case, it's cyclohexane. And then you just follow that up with carbaldehyde. And I think it's one of those where you either forget carbaldehyde or it seems too simple. Right? Like if I give you a 4-membered ring with an aldehyde popping off of it, then it's just cyclobutane carbaldehyde. Right? Nothing fancy. And then that's probably a case of one of those, I knew it, I overthought it, there was something there that looked a little bit more complicated, but it made sense, so I think that one instead of the easy one. Right? Don't let that be it. All right, so I've alluded to that list that was in the chapter notes for alcohols in terms of priority. If you go back and look at that list, what you'll find is that aldehydes take priority over the ketone. Right? That's a really important thing to note, because if that's the case, it means that we now need to learn how to refer to the ketones as their functional group name. All right, so just to annotate the notes a little bit, an aldehyde containing a ketone is called an oxo. That's the new thing, oxoalkanal. right? And so what that's pointing to is the fact that the ketone as a functional group is referred to as the oxo group. And so just to, so you don't have to flip back and forth, I'll write here that aldehydes have priority over ketones. Right. Now, of course, the exercise is going to be giving you an example in which both of these are present in the same structure. Something like this. And yeah, you're going to have to commit to memory, right? The aldehyde takes priority. It's treated as such. That makes this carbon automatically carbon 1. 2, 3, 4. So that means the ketone carbonyl is a carbon 3. That would be 3-oxo. So in this case, this would be 3-oxo. 4 carbons is butanal. Right? Because aldehydes are automatically at the end of the chain, then we don't need to introduce the number to indicate where the aldehydes start. Now there are also varied substituent names worth going over. It is not uncommon to see the ketone as a group popping off of a larger architecture. Okay, if you have a ketone popping off a bit of larger architecture, you might see this term alkanoyl, A-N-O-Y-L. If the R group of that ketone is known, and it's known to be a methyl, such as in this example right here, this is known as an acetyl group.